I've just arrived at Boulby Mine. We've just been inducted, safety, and now we're going to actually head down because we have to take a lift 1 kilometre underground.
Welcome underground.
I can really understand why mining is such an engineering field.
Yeah.
Because you just have to constantly problem solve and sort of look out for risk and always just safeguard yourself.
The main driver for us was radiation. So we are currently experiencing a 1/1,000,000th reduction of the cosmic ray rate that you get on the surface.
1/1,000,000th.
So as in, there is 1/1,000,000th the flux of cosmic rays here than there would be on the surface. But if you're doing like super sensitive particle physics experiments or related physics experiments, then if they are very sensitive, they're going to pick up background radiation. So if you can remove all of that noise, then you've helped your experiments a lot. Yeah. Muons are naturally occurring particles. They're produced when particles from space interact in the upper atmosphere. They produce showers of muons that kind of cascade down to Earth. I often like to compare muon tomography to large-scale X-rays. It's effectively what you're doing, right? So with an X-ray, you shine it through a body, and from where it gets absorbed, you can see the bones and whether there's breaks in the bones. So with muons, from where it gets absorbed, passing through a mountain or a building or a tunnel, you can see if there's any breaks or gaps. So you can then use...
Should we be getting any muons down here?
We get some. We get approximately, for every 1,000,000 muons that hits the surface, only one of them will get as far as we are down here. So, yeah.
So that rock is really doing something above us.
Absolutely, yes. These blue ones here, this is the tsunami early warning system.
So where would these detectors be placed?
Ultimately, they're destined to go in Tokyo Harbour.
So technology that is useful in Japan is being researched here. Why?
Absolutely. Because of our location, which allows us to test this experiment, a large amount of the tunnels of this mine go out under the sea. And this equipment is sensitive enough that even at a depth of over 1 kilometre, you can detect the rise and fall of the tide. Because even water affects muon absorption rate, as the tide goes up and down, you can detect that with muons.
So before there's a tsunami, there's like a real sucking of water
Absolutely,
away
yeah,
before a
characteristic recession, and then the big... So if you can detect that even a minute earlier in an emergency situation, could save a lot of lives, right?
So you are detecting how many muons are coming from space through the sea.
Yep.
And if there's a little bit of sea, because there's been a recession of seawater because a tsunami is about to come, you can detect that from counting the muons.
Yes.
And that's how a tsunami detection system works. Oh my God, mind blown.
The deep, unique and extremely clean environment of Boulby Underground Lab was originally designed to detect dark matter only. But since 2020, this lab has been expanding out into the active mine itself to explore other engineering ideas.
So the section of the tunnel that we're in kind of belongs to the lab, and this is what we call the outside experimentation area, or the Mars Yard, because that name sticks a little bit better. We use this area as an analogue for the surface of Mars. When we get rovers doing their testing, they drive around up here. And that is because the geology is like surprisingly similar to the subsurface of Mars. This is an experiment called Biosphere. It's in its early stages, but it's looking at how you would set up a field laboratory or a field hospital on the moon, on Mars, that sort of thing.
Imagine you're on the moon and you need a hospital. This is what it might look like. And so the purpose of this is to really make sure that it stays clean and habitable.
Especially if you have a serious injury on the moon. At the minute, there are no facilities. Like the nearest hospital is several million miles away.
The conditions down here may resemble the surface of Mars or the Moon, but Ed also showed me another unusual engineering idea, this time involving the topic of renewable energy.
It's a lot of developing equipment and tools for the possibility of blah, blah, blah.
Some of it, yeah, some of it is like actual development of tools. So the Rosalind Franklin rover, which has been delayed many times, but hopefully launching soon. 3 of the experiments on that were actually tested right here at Boulby. So actual stuff as well as future development stuff.
Oh, Ed, I must say, it is hot.
It is hot. Should we go
I
back
can
inside?
literally, yeah, feel.
The resource experiment, which I'm responsible for, which is the energy storage one.
Oh yeah. What's that about?
So the idea being, as the UK moves to more and more renewable sources of energy, you run into a slight issue in that supply doesn't always meet demand. In some cases, supply can actually exceed demand on the grid, and the grid is not built to deal with that.
You can't always predict when the wind's going to blow and
That's
the sun's
exactly
going to
it.
shine.
Yeah, and if people are boiling all their kettles or not. You need a way to be able to smooth out those peaks and troughs, and conventional batteries just don't cut it on the scale that you need. We're talking like national grid levels of energy. One current solution that's used in Wales is Electric Mountain, Dinorwig. Have you seen that one?
Is that the gravity battery?
Sort of, yes. So it's the hydroelectric system.
Okay.
Where when there is that excess energy, they use it to pump water to the top of the reservoir.
Yeah.
Yeah, and then when they need it later,
storing up gravitational potential energy.
Yeah, and you can release that, turn a turbine, get your energy back out.
So simple, so...
That's it, isn't it?
So genius.
Yeah. So what we're looking at here is similar principle, but using compressed air instead of water. So when you have that excess energy, you can pump loads of air into a big cavern in the rock, and compress it. And then when you need that energy later, you release it, turns a turbine, gives you the energy back out. Same principle.
So what are we actually looking at?
So we're looking at small scale test of this principle. So you could create these holes using solution mining, which is dissolving that rock using water.
So you're actually making the bulb shape using these 2 tanks of water, essentially?
Yeah, yeah.
And where would the bulb be? There's a hole
there. There is
there.
one right underneath that hole, about 2.5 metres underground. And it looks like that, because that is a scan that I did over this weekend.
So water solution has created that shape. It's almost like a little carved out jar to accommodate compressed air.
So the stage of this project that we're at currently is how do we best make these shapes, and what shapes do we get when we make it in different ways. So there's, I think, 6 boreholes around here. This is the second one that we've done so far. And yeah, we're testing with different inputs and outputs, different flow rates. How does that affect the shape that we get at the end?
You just basically get to have a scientific play. It's really cool. We made it back to the surface. Just learned so much. Just have an even greater respect for engineering and science and STEM. And I love my job.